All right, folks, let's do section 3.6, which is all about inverse functions and some derivatives and rules we can get once we know how to work with them. So obviously we have this just basic definition of an inverse, which is super important to remember. If for some reason you don't, we're going to use it for like a trick the entire time. Not a trick, but it's a good property. And if f of x has an inverse, and we obviously denote it with what's written in red there, the big relationship you need to remember for today is if I were to take the inverse and plug it into its original function, or even if I took the original function and put it into the inverse, that would give us back the original input. The inverse and the function undo each other, and we're left with the original input. So everything the function does to the input, the inverse undoes it. So that's a huge fundamental fact that we're going to use. And once we know that, let's just kind of look at the relationship between a function, its inverse, and the derivatives there. So what we just went over again by definition, if I put the inverse into the original function, I will get the original input back. So then we can look at the derivatives there then. So what if I were to look at the derivative of the left side? Well, the derivative of the left side, so the derivative with respects to x of this composition of functions here. And the composition is kind of special because it happens to be an inverse put into its own function, but that's still a composition of functions. Well, if this function on the left is x, well then their rates of change better be the same because they are the same exact function. And what's super nice is we know that the rate of change of x in respects to x is just a 1-to-1 ratio, right? Whatever I change this little x by, well, that's what's going to change that little x by. So that's really nice. We know the right side is 1. So as I was mentioning before, if I was trying to find the derivative of the left side, this left side is just a chain rule. So we know how to use the chain rule. We would do the derivative of the outside function. So in this case, the derivative of f with the inside function as its input. And then we'd have to multiply it by the derivative of the inside function. And we don't really know what the derivative of the inside function is right now. But what we can do is just solve for that. And the way that we'd solve for that is divide both sides by the derivative of function f with the inverse as its input. So that would leave us on the right side then with 1 over that stuff we wrote before, which was the original function's derivative with its inverse as the input. And we've actually solved our first super important rule today. The derivative of an inverse of a function is the reciprocal of the derivative of the original function, but evaluated at its inverse instead of at the point x. So super huge thing to get in your notes, big idea for today. So make sure we know how to define the derivative of an inverse function. So once we know that, though, we can use it to do other things, like find derivatives of the natural log of x, which I know we all think is probably the most natural thing to do next, right? So let's just look at what I have written down here. So if we were our goal is to find the derivative of the natural log of x, which we don't technically know right now. But the idea is I'm going to start with two smaller functions, e to the x and the natural log of x, because what I know is if I were to compose these functions, if I was going to put g into function f, that would mean I would have e to the natural log of x. And I know that that would just give me x. I'm going to save it and not show the other one, so the reverse composition, but that will also give us x. So we know that these two are inverses. And that's a nice little thing for us to do. So in other words, if we started with the function, then if we composed them, and we said composing those functions would be e to the natural log of x, well, if I looked at the derivative of that function, the derivative of the natural, or e to the natural log of x, well, that should be equivalent to the derivative of x with respect to x, because again, this function is x. We just said that up top, so they're equivalent, so their derivatives have to be equivalent. So what we notice though is that this, again by definition, was a composition. So if we wanted to find the derivative, we can use the chain rule. So the derivative of the outside, and we know the derivative of e is just e, of the inside, so of its original input, times the derivative of the inside. Now, I don't know what the derivative of the natural log of x is. That's what we're trying to find. But I do know the derivative of x with respect to x is 1. So again, we want to find out what is the derivative of the natural log of x. So we are going to isolate this term using division. So the derivative with respect to x of the natural log of x would be equal to 1 over e to the natural log of x. And then by definition, again, right, these were inverses of each other, so they would equal x. So there's our next important rule for today. The derivative of the natural log of x is 1 over x. Moving forward, we are going to find the derivative of arctangent of x, or the arctangent, or sometimes I might refer to it simply as the inverse of tangent. But by definition, just reminding you that arctangent of x is the inverse of tangent of x. So with this one, I'm going to start by using some notation, I believe. Yeah, let's do it that way. So let's just go ahead and define y, our function that we're trying to find the derivative of, as the arctangent of x. So what we already know is, by definition, if I were to take the arctangent of x and put it into the tangent function, they would undo each other, and I would just get x. So I guess this is just the function we're trying to find the derivative of. I'll just keep writing that notation. So, okay, well, let's just look at the derivatives then. So if I were to take the derivative of the left side with respect to x, and again, the derivative of this function on the left side, well, that function on the left side, by definition, is x. So that should be equivalent over here, just two different ways of writing the same problem. And again, as we've been seeing, we know the right side is equal to 1. So what we can then do on the left side is use the chain rule, because we have a composition, right? And it just happens to be that that composition is inverse, which is why we know that reduces to x. But we don't simplify the left side. The derivative of the outside, right? So the derivative of tangent, we know from our work before, the derivative of tangent is 1 over cosine squared of the input. And in this case, our input is arctangent of x. And then we'd have to multiply that by the derivative of the inside. And again, that's what we don't know. We don't know the derivative with respects to x of the arctangent of x. So we're going to have to start to simplify to try to get that term alone. We need to find out what is the derivative of the arctangent of x. So I'm just going to highlight that. That's what we want to get alone. So the first thing I'm going to do is I'm going to multiply the left and the right side, I guess, by the denominator over here. I don't want that on the denominator. So if I multiply the left side by that, and if I multiply the right side by that, we can obviously see on the left side that those will cancel. So we would obviously be closer to where we were trying to go. We're trying to find the derivative of the arctangent of x, so that would be our left side. So the derivative with respects to x of the arctangent of x would equal cosine squared of the arctangent of x. Now that is not how we're going to leave it though, because the arctangent of x, first of all, is just not something we really work with on a daily basis. Not that it's a bad function, but we don't work with it. It has some asymptote. It's just not nearly as nice. And we also don't want to define the derivative of arctangent of x using arctangent of x. So quickly, I want to try to keep with the theme of inverses today, and like we should kind of get some more canceling. I don't really want to use arctangent of x over here, so we're going to take a moment just to look at a Pythagorean identity. So what we know, sine squared of x plus cosine squared of x should equal 1. Now I'm just going to rewrite that by dividing everything by cosine squared of x. When I divide everything by cosine squared of x, And we'll kind of rewrite some things. This I'm going to rewrite as tangent squared of x, right? Sine over cosine is the tangent function, and then cosine squared over cosine squared is 1. And we could rewrite the right side as secant. I'm going to choose just to leave it as 1 over cosine squared of x, because I want to keep the cosine in there. Now, we will see that we could have applied this identity a little bit earlier, too. We see this is what we kind of canceling over there. But what I'm going to do then is just take the inverse of both sides and just flip everything over. So like the inverse of that side and the inverse of this side. I know that's kind of bad notation, but that'd be 1 over tangent squared of x plus 1 would equal cosine squared of x. Now, this might just seem like you're following along randomly, but like, why did we care to do that? Well, what we can see now is I could take this cosine function, which is up here, and rewrite it, instead of using cosine, using tangent as the main function. And why that's nice is because the input that I would have put into the cosine function is the arctangent. So if I can, instead of putting the arctangent into the cosine function, I could rewrite that and put the arctangent into the tangent function. So I'm going to go ahead, I'm going to take this line right here, and we're going to rewrite that. So we know the left side, and we're going to rewrite it using that identity that we just did, that cosine squared of x is equivalent to 1 over tangent squared of x plus 1, or 1 plus tangent squared of x, doesn't really matter. So on the left side, we still have that derivative term, the derivative of x, or in respects to x, of the arctangent of x is equal to, now here we're going to apply that identity. Instead of cosine squared, we're going to rewrite that as 1 over, and I'm going to put the 1 first, 1 plus tangent squared of the input, right? Now up here was x, so we wrote it as x, but it's not x. We have to apply it to our problem, and our input is the arctangent of x. And then we see, like, we've made it super far. This is awesome because we just put the arctangent into the tangent. Now, it might be helpful just to rewrite that right side one more time to see where we're going to get x squared from instead of just x, because tangent squared means take tangent, multiply it by itself. So I'd take tangent with its input, which is the arctangent of x, and I multiply it by itself. So the tangent of the arctangent of x. So by definition, if I put the arctangent into the tangent, that gives me x. If I put the arctangent into the tangent, that gives me x. So I would rewrite, I would rewrite the right side, let's do it here, as 1 over 1 plus x squared. And that is our derivative rule that we will finally stick with because it just looks way nicer. Sorry, I can summarize that for you just a little bit better. So in other words, the derivative of the arctangent of x with respects to x is equal to 1 over 1 plus x squared. So now I want you to look in your notes, and I'm going to skip forward just a little bit, actually. I want to do example number 6, or practice number 6. I forget what I called it in your notes. But please go find that table. First of all, there's just some good applications of the kind of like the inverse rules and the inverse derivatives, but also kind of just, it gives another way of us understanding what we're looking at, why these rules are working, and a little more conceptual picture on a graph. So if we look at 6a, we have this table which gives us inputs, it gives us our function, and then it gives us the values of the derivatives at that function, or at those points. So the first thing it wants us to find is f of 2. So the value of the function at 2, we can see from the table, is 4. They want us to find the value of the inverse of 2. Now this is a good moment just to like make sure you understand the inverse, right? They're saying, well, this was the output originally. So if I got the output to be 2, what was the original input value, right? It should be our x value back. So the original input value, if I got out 2, that means I must have put in 1. And then lastly, they want us to just summarize the derivative value of the function at 2, and from the table, that is 2.8. Now, they want us to calculate that, or we're calculating those things, because then we can use it to find out that second thing below, which they want us to find the value of the derivative of the inverse at 2. It is important to point out the notation here. So we're looking for the value of the derivative of the inverse. So we put the inverse in parentheses, note that it's the derivative, and then of x. And in this case, they want us to find it at 2. So we know our rule for the derivative of an inverse. It is 1 over the derivative of the original function, but evaluated at the inverse of the point and not at that point itself. So we'll simplify just a little bit, and this is why we looked up top. So what is the value of the inverse at 2? Well, we said before that was 1. And then the derivative, or excuse me, 1. And then we said the derivative of 1, we can see from the table, is 1.4. So this would be 1 over 1.4. So that's the value of the derivative of the inverse function at 0.2. Now moving below that, part B, sorry, I guess I have part B below. So part B, first of all, is just a good question. So let's go ahead and do some of that work for a moment here. So they want us to find the equation of a tangent line to point P, and we can see that point P is on, right, is on our function because it's in our table. So point P, and then they want us to find the tangent line of the inverse of that point. So kind of, again, digging a little bit deeper into the relationship of the function and its inverse. So we could find the tangent line to point P pretty quickly here. And it's a good exercise. So point P is at 3, 8. So if we're going to find a tangent line and we have a point, we should just really use point slope form. So point slope form. So we'll take y minus 8. And then the slope of that line, so by definition, the slope of the tangent line is the derivative at that point. So point P is on the function, so the slope of the tangent line would be the derivative of the function at that input. And then the rest of our point slope form, minus 3. So, well, we know the derivative of our function at 0.3. That's in the table, and that's given to us as 5.5. Now, if we were going to go on, and the other part of letter B is asking us to find the equation of the tangent line at point Q, which is just the inverse of P. So the inverse of P, so point Q, that's flip-flopping the inputs and the outputs, so that's at 0.83. And they want us again to find the equation of the tangent line. So we'll use our point slope form, so y minus 3. Now the slope of this line, point Q is on the inverse function. So we'd have to use the derivative of the inverse function at our input. Now this, we'll have to apply our rule that we already know. How do I find the value of a derivative of an inverse function? Well, we know that's 1, so I'm going to just calculate this by itself. 1 over the original function's derivative, but evaluated at the inverse as the input. So this, and I'm choosing to write this separately for this reason, we will see as 1 over the derivative of function f at 3. So let's go ahead and rewrite, and sorry, one more time, we know therefore that's 1 over 5.5. So finishing up, we can now write the equation of our tangent line, y minus 3 is equal to 1 over 5.5 times x minus 8. Now, sweet, that's just a great problem in itself, just to make sure we're kind of remembering some of these basic fundamental understandings. But what they're actually hoping that we see a little bit further, though, is what we see here is that the slope of this tangent line of the function was 5.5, and then we see the slope of the tangent line of the inverse was its reciprocal, right? They're really trying to get us to see the fundamental idea of our inverse derivative, right? If we go back and find what we wrote way before, right? The derivative of an inverse is the reciprocal of the derivative of the inverse function. So that's what they want us to see here, and I think we should take a moment to look at that a little bit more. So we can see that the slope of the function is the inverse of the slope of the derivative. I do want to look at that on a graph that I've prepared. So I have a bunch of stuff on this graph that I've prepared, and I'll link it so you can pull it up in front of you. So the first thing I have prepared, this is just the values of f of x. And I hope we see the pattern. I think it's going to be a little bit easier right now to look at it as a curve. So I'm going to go ahead and fill that in as a curve. Now, we could calculate the derivative. I mean, the derivative doesn't help us too much. We just want the values of the derivative. That's what was given in the table. So I'm just going to take the values of the derivative. Sorry, that was the wrong thing. I'm going to take the values of the derivative. I'm just going to plot them here. Then I'm going to go ahead and just visualize that as a curve. But once I put in that curve, I can start to see that that relationship is something I should kind of recognize. When I plot those values, it looks like it's a reflection right over the line y equals x. So we can see that huge idea of the inverse. So if we kind of visualize the problem that we just did, what we were supposed to do, so I'm going to get rid of our reflection line. I'm going to get rid of just that for now. We're supposed to find the tangent line at 3, 8, right? So there's 3, or sorry, excuse me. There's 3, 8. So if I fill in the tangent line there, I'm just going to go ahead and get rid of the curve for a second. We can see this is our tangent at the point 3, 8. If I do the same thing and try to find the tangent at the point 8, 3, which is its inverse point, so it's on the inverse function, I have that tangent line here. I'm going to get rid of the curve just for a second. And what I see, therefore, again, same thing. I put that line back in. I can clearly see that this line, the slope of that line, just looks like it's the inverse of that line. So we can see that the slope of an original function and the slope of its inverse have this reciprocal relationship, 1 over. They are reflections. We can see that in our original definition of the formula. So I think it's nice to see as a graph. We're going to move on from that. So the next thing you need to see, though, is number 5 is not actually really a practice problem. It's more so actually another proof that you need to actually go over. So you need to watch this one. And so the idea here is that we're supposed to find the original, we're supposed to find the derivative of f of x. And what we see here is if we're going to find the derivative right now, we'd have to use the chain rule. But we'd start with the derivative of the outside, and the derivative of the outside would be the derivative of arc sine of x, and we don't know what that is. So we're going to take a moment to prove this. We got to just know what that is, and maybe we'll come back and finish the problem. But that's what we're going to do for this part here. So to make some notation easier and kind of have everything look a little nicer, let's just go ahead and define this function y as the arc sine of x, right? So the inverse of the sine function. So what's the derivative of that? That's eventually what we're going to try to go find. But again, just kind of looking at our important relationship for today, if I were to put that function y back into itself, right? So the sine of the arc sine of x should just equal x, right? Let's just keep that in mind. That's kind of that big idea that we've been using for our proofs today. So why do we care? So then what we can do is let's kind of go back to the original kind of flavor of how we were finding these derivatives today with our inverse idea. So what I could do is I could ask myself, well, what is the derivative of that function then? So what is the derivative of sine of y? Now this is in terms of y, but sine of y, we just set up here, was x. And again, I'm choosing to use y instead of arc sine of x, so it makes the notation a little bit easier and it makes it less writing. So again, right side we know is 1. That's super awesome. And the left side of the function, or the left side of this equation, excuse me, we can see is a chain rule. We have a function y in another function sine. So let's go ahead and apply our chain rule. So our chain rule would say the derivative of the outside of the inside times the derivative of the inside. And I don't know what the derivative of y is in respects to x. That's what I'm trying to find out. I don't know what the derivative of arcsine of x is. So the derivative of y, right, which is the arcsine of x, should equal 1 over cosine of y. But the problem is that's not in terms of x. We're supposed to describe how arcsine of x would change if we changed x, and right now we can see that cosine is relying on y. So we can't have that. We got to keep going is what I'm saying here. So we have to somehow be able to go back and re-represent the cosine of y and find an equivalent value or rewrite that somehow using x. So we're going to have to go back to like a little bit of trig here. So just rewriting what we originally started with, our idea was the sine of y, right? The sine of the arcsine should just be x. So if we draw that on kind of like a little smidge of our unit circle for a second here. So we'd say, okay, our angle is y, our hypotenuse is 1, and then we have this opposite side, we have this adjacent side. Now, we know from what we set up top that the sine of y was equal to x. Well, if we're on the unit circle, we know that sine is the opposite side over the hypotenuse. So the opposite side over the hypotenuse is equal to x. So therefore, we're told that the opposite side has the value of x. So if we wanted to somehow then try to represent the cosine of y, right? That's our problem here. What is the cosine of y? How could we represent that in terms of x? Well, let's look at our unit circle here. So cosine of y would equal the adjacent side over the hypotenuse, which is just 1. So if we can find the adjacent side of that triangle, we're great. We can represent cosine in terms of x, we can represent cosine in a different way. So we're just going to use the Pythagorean theorem quickly to find that, right? So the adjacent side, which I'm just going to abbreviate as a squared plus x squared should equal 1 squared. So solving that, we will see that a, the side length, right? Because we want a side length, so I'm going to go ahead and just drop the negative right away, would equal the square root of 1 minus x squared. So in other words, instead of the cosine of y, which was the problem, the cosine of y was not represented in terms of x like we were supposed to. So instead of the cosine of y, we just gave ourselves permission to represent that as 1 minus x squared. Sorry, the root of 1 minus x squared. And again, that was just by our definition of the unit circle. The cosine of y is equal to the adjacent side over the hypotenuse, and this was our adjacent side. So finally, we've made it. We can go back to our original original derivative. I'm just going to go ahead and rewrite it. And then we were trying to figure out the change in terms of x and the way that we wrote it up top. I guess I can do that first. The way that we wrote it here, whoops. We said it was just change in y was 1 over the cosine of y. So let's replace the cosine of y with what we found it out to be as the square root of 1 minus x squared. And if we really want to be nice to ourselves, we'll finally get rid of that change in y and say, well, what was our function y? Well, function y was the arcsine of x. So the derivative with respects to x of the arcsine of x is 1 over the root of 1 minus x squared. Last couple of examples, a lot quicker, a lot more straightforward. Here they want us to find derivatives. So what is the derivative of this function? Well, we can use our chain rule. So the derivative of the outside, we know the derivative of the natural log would be 1 over x. And in this case, so 1 over the input. So the derivative of the outside of the inside times the derivative of the inside. And this might be a great time to really think about alternate notation if it's hard to think about what that input was. We could just say u was equal to x squared plus 1. So if we wanted to find the derivative of the natural log of u, it's a little bit easier to see that this would be 1 over u times the derivative of u. And so we just go back and replace 1 over x squared plus 1 times 2x. Right? This might make it a little more easy to apply that straightforward rule that we learned in the notes. Next one, go ahead and use our product rule here. We see it's t squared times the natural log of t. So left d right, so left d right plus right d left. So we'd obviously want to simplify that. So that's just t plus the natural log of t times 2t. That's good enough for now. This one doesn't look super friendly, but that's okay. I'm probably gonna write this in separate notation right now. So let's just go ahead and say this smaller thing, u, is 1 plus the natural log of 1 minus y. So I could calculate the derivative of that by itself because I'm not going to need it. It's the inside function. So the derivative of this, the constant won't matter. So the derivative of this is actually another chain rule in itself almost. So the derivative of the outside, so the derivative of the outside is 1 over x, but in this case x is 1 minus y, right? Times the derivative of the inside, and the derivative of 1 minus y is just negative 1. So u prime will equal negative 1 over 1 minus y. So let's go back to our original problem then. So if we're going to try to find the derivative of the square root, now I'm just calling this u, which is a little bit easier here. So h prime, that's what we're trying to find here. So I'm going to rewrite that as u to the 1/2. So we know the derivative would be 1 over 2 root u times the derivative of the inside, right, to use our chain rule. So the derivative of the outside times the derivative of the inside. Go back and replace some stuff. U we defined as 1 plus the natural log of 1 minus y. And then u prime we said was negative 1 over 1 minus y. So that'd be negative 1 over 2 times 1 minus y times 1 plus the natural log of 1 minus y all over the root. The derivative of the arctangent of tangent squared of x, or sorry, of just t squared. So the derivative then here, so the derivative of the outside, we know the derivative of arctangent, that was 1 over 1 plus t squared, or x squared, or whatever the input squared was. Now in this case, our input is t squared. So the derivative of the outside of the inside times the derivative of the inside. Again, it's helpful to see we said the derivative of arctangent of x. The derivative of that was 1 over 1 plus x squared. So whatever the original input was being squared. So whatever the original input was being squared. That's all.